Math 2414, Calculus 2, Calculus 1 review, integration by substitution. Get the zoom working here. All right. Integration by substitution is the last Calculus 1 topic I'm going to review. I chose the topics to review that I did because I know what students typically struggle with transitioning from Calculus 1 to Calculus 2. But I should warn you that this is not the only thing people struggle with. Algebra and trigonometry are the two big things as well. But let's review integration by substitution. We're going to integrate 3x plus 1 to the 5th power dx. Now, you should have seen substitution already, but if you were in Calculus 1, it may have been one of the last things that you saw. And so it's the thing that you had the least experience with. Substitution is not going away. Almost every time we do an integral, there will almost always be some type of substitution involved. So it's imperative that you get comfortable with recognizing when to do it and how to execute it. I don't know what your Calculus 1 teacher told you about substitution, but here's how I look at it. There's two ways to think about it. Actually, before we get into those two ways, let's just jump into this and naturally develop the questions I'm about to throw out at you. If I wanted to integrate this, it would be nice to have a rule, and you'll notice I still have 4 integral rules left over from the previous video. That was intentional. This function is something raised to a power, so we have a rule for that. The rule says if you have u to the n power, raise the power, multiply by the reciprocal of the power, add some constant of integration. So can we just do that? Can we just add 1 to the power and multiply by that reciprocal and then add a constant of integration to it? Well, it sounds good, but remember, this is asking what's the antiderivative, meaning if we take the derivative of that, do we get that? So let's just check this answer that we got by just applying the power rule since this has a power. Well, if we check it, we got to take the derivative. We have a constant multiple of a function, and so the derivative, the constant would stay there. And then when we take the derivative of this guy, which invokes the chain rule, we have an outside and an inside. The derivative of the outside would be to bring down the power and lower it by 1. Chain rule says leave the inside alone, and then multiply times the derivative of the inside. The derivative of 3x plus 1 is just 3, and then the derivative of this constant is 0, so it's gone. So will this get us back to where we started? Well, let's see. The 6's cancel. That's good because we didn't have a 6. But the 3 is still there. And of course the plus 0 is ignorable. So no. Angry face. That is not what we started with. Which means that this was not the antiderivative. When we took its derivative, it was 3 times as large as it was supposed to be. So why did that happen? Is this rule wrong? No, the rule's not wrong, but the use of it was. So why was the use of it wrong? Well, that rule says if you have a variable to a power, that's what you do. This is not a variable to a power. This is an expression to a power. It's not a single letter. It's a single letter with a bunch of stuff attached to it, namely the 3 times and the plus 1. So this rule was not meant to be used on this problem as is because the structure of this integral did not match the structure of this in terms of the base and the exponent. The base being a single letter, du, that was not a single letter. It was 3x plus 1. So here's the 2 comments that I wanted to make about substitution. Number 1. Integration by substitution is really just integration to undo the effects of the chain rule. Where did this 3 come from? It came from implementing the chain rule. So if we take the chain rule when we do the derivative, then we need to quote-unquote undo the chain rule when we take the antiderivative. So that's observation number 1. Observation number 2 I've kind of already made. Structurally, this integral sort of looked like that one, but the difference was critical. The base here was a single letter, the base here was not. That created the problem with the chain rule. So how do we fix that? And how do we not do this? Full disclosure, when I took calculus in high school, this was a spot that I got to where I almost gave up math. Because for about a week, I didn't get it. finally another student said, well, think of it this way, and it clicked, and then everything was okay. Here I am 30 plus years later, chair of a math department and teaching Calculus 2 on YouTube. So if you struggled with substitution, I completely understand. Hopefully I can make it as easy as possible. All right, so how do we do substitution? Well, first is identifying the substitution and then implementing it. To identify a substitution, and here's what a lot of teachers don't say. The goal of substitution is to transform an integral that doesn't match a rule into one that does match it. Structurally, this is a power. It's a chunky something to a power, but it's the integral of a power. This is the rule for the integral of a power. So how do you pull off the substitution? Well, you look for the part that is in the place of the u, and you're going to call it u. So you got to start by identifying who is in the place of the u in the rule that I'm trying to use. In this case, that u is sitting right there. If that underlined expression was just the letter u, it would match this exactly. We could do this rule and we would be good. So you start off a substitution by finding something and saying, I'm going to let u equal that expression. So we're going to change it and say let u equal 3x plus 1, which is great, because if I put a u here, it's going to say u to the fifth. It has the correct structure. We can use this rule, but we're not out of the woods yet. Because if I have a u here, I have to have a du there, and I currently have a dx. So how do we figure out what to do with the dx? Well, I need to figure out what to replace it with. Now, how are we going to do that? Well, to figure out what dx equals, I need an equation with the dx, and currently have an equation with an x. So let's differentiate this equation. Now we're going to differentiate it with respect to x. If we take the derivative of u with respect to x, then that is equal to, well, what's this derivative? It's just 3. Now that doesn't quite get me what I want to know, because the dx is trapped down here in the bottom of this notation, and this looks like a fraction, and it's not, but it kind of behaves like a fraction in the sense that we can multiply both sides by dx. It's not really what's happening, but it's a gimmicky way of saying du is equal to 3 dx. And now we're getting somewhere, because I need to know something about dx, and here's something I know about it. 3 times dx is equal to du. Most people, when they're doing substitution, bypass this step. What they do is just say derivative of u, which is not really what this is, but for our purposes we can say derivative of u is equal to, take this derivative dx. Du is equal to the derivative of this dx. Now, does that mean I can just take the dx and replace it? Well, sort of. What happens next? There's 2 schools of thought, and there's one school of thought that I have always used, but I think I'm going to try shifting that school of thought briefly. And I'm going to have to concentrate on that throughout the rest of the semester every time we do a substitution. I know I'm going to replace this with a u, but what am I going to replace dx with? Well, I can only replace dx with something that it equals, which means I need an equation that says dx equals. If I multiply both sides of this by 1/3, I get 1/3 du is equal to dx. And that is what I will substitute for dx. The choice of the original substitution is driven by what is in the place of the u in the rule that I'm using, in this case 3x plus 1, and then you figure out what to replace dx with by taking the derivative of both sides, du on the left, dx on the right, and then solving for dx. So now we can say the following. The integral of 3x plus 1 to the fifth dx. The 3x plus 1 becomes a u, so this becomes the integral, and I'm going to write all the u stuff in green, of u. Now the fifth power was not part of the substitution, so it's still there. And then the dx is going to be replaced with 1/3 du. 1 second, folks. 1/3 du. All right, well, this almost structurally represents integral number 1. There was an integral rule that I didn't throw up there, but it's one you should be familiar with. If you have a constant factor inside of an integral, you can pull the constant factor out. So if we pull out the 1/3, we get a u to the 5th du. Now this is in the correct form to use rule number 1. Rule number 1 says, there's the 1/3, add 1 to the power, multiply by its reciprocal, and then something's fishy here. Let's take this to the end. Plus c, and we get 1/18 u to the 6th power plus c. This isn't seeming right, but we'll run with it. My spidey senses are tingling. I feel like something has gone astray and I can't spot it, so we'll just keep pushing this until either it's right or it breaks. So do we have our antiderivative? Well, sort of, but not quite, because our integral was in terms of x and this is in terms of u. This is where we undo the substitution. U is holding the place of 3x plus 1. Yeah, this is right. And so instead of 1/18 u to the 6th, it'll be 1/18 times 3x plus 1 to the 6th plus c, and I claim that this is the correct answer. Let's review what happened with the substitution real quick before we check it by taking the derivative of that guy. This integral sort of looked like that one, but instead of a single letter, it had 3x plus 1. If you know your rules, and you can match your rules structurally to an integral, it will tell you what the u should equal. It won't always be that straightforward, but a lot of times it is. If I set up a u here, take the derivative of both sides by saying du equals the derivative, which was 3, times dx, which is really this crossed out line cleaned up a little bit, and then solve for dx. I never actually wrote that, but let's solve for dx. Then it tells us what dx equals, which means I know exactly what to replace the dx with. This should transform it to an integral that perfectly matches the form of the rule. Play out the rule, undo the substitution, and it should be over. Let's check it real quick. To check it, we'd leave the 1/18 alone, and then we would take the derivative of 3x plus 1 to the 6th, which means we would implement the chain rule, starting with the power rule, bring down the power, leave the inside alone, lower the power by 1, and then the chain rule would swoop in at the end and say times the derivative of the inside, derivative of 3x is 3, the derivative of this constant is 0, 6 times 3 is 18, which cancels the 1/18, leaves us 3x plus 1 to the 5th, which was the original integrand. I don't think I ever wrote the word up here yet, but I keep saying the word integrand. It's the technical name of what you are integrating. All right, so in the next video, we'll do a couple more examples, and I may have 1 or 2 more follow-up videos after this one to work out some more examples, because substitution's not going away, ever. Ever, ever, ever. Not even in Calculus 3.